So here's another problem that's based on series. It's from the 2009 BC free response set. This is problem 6, another no calculator question. And they were nice enough here to actually provide us with the Maclaurin series representation for e to the x. That's something you're going to want to have memorized. You don't want to bank on the College Board actually providing that to you. But they were nice enough to do that in this particular problem. And then they tell us that the function f is defined by this function right here, and it's that way for all x's except when x is equal to 1. They tell us what f of 1 equals, and then they want us to, in part A, write the first 4 non-zero terms in the general term for the Taylor series for e to the x minus 1 quantity squared about x equals 1. So our Taylor series is supposed to be based at 1, so we're going to have x minus 1s raised to powers all over the place. Kind of weird that we're not really dealing with f right away. We're dealing with this one little component in f's numerator. So what I did, just to kind of provide some notation here, I just called g of x e to the x, and then h of x is this function right here that we're trying to find a Taylor series representation based at 1 for. And then I can relate h and g. H of x would then be what g of x is, but with this quantity replacing the exponent, replacing the x. And if you have a Taylor series representation for g and you want a Taylor series representation for h, what you can do is you can replace the x's in the series representation for g, so replace this x, this x, this x, and this x with x minus 1 quantity squared. So that's what I've done right here. H of x is going to be equal to this, and again, simply replace all of the x's in the series representation for g with what we have going in place of this x in g when we define this new function h. And then I just kind of cleaned that up a little bit, so I just used power to a power a couple times, and I ended up with my first 4 non-zero terms, and then my general term. This series is based at 1, right? We see those x minus 1 raised to different powers all over the place. We now have a Taylor series representation for the function that's defined here in part A. In part B, we want to use what we've done in part A to help us develop a Taylor series for this function f. So now we're dealing with f. So what I went ahead and did is I took the answer from A, the series representation for this, which I named h of x, and I put it in place of that term in the numerator. What you'll notice is a plus 1 from our series for e to the x minus 1 quantity squared, and then a minus 1 sitting at the end of that numerator for the function f, and then it's just all over x minus 1 quantity squared. Well, these 1's are going to cancel. And then what you can go ahead and do is you'll notice a common factor between every piece that's left in this numerator. You'll notice a common factor of x minus 1 quantity squared. So if you factor out that common factor, take it out of this term, you're left with 1. Take it out of this term, your power goes down by 2. Take it out of this term, your power goes down by 2, and so on. I did express one extra term here. I realized that the first term canceled with this, so if I want the first 4 non-zero terms, it was a bad job at underlining, but if I wanted the first 4 non-zero terms, I'm going to have one more piece represented since this first piece canceled with that minus 1 at the end of the numerator in the function f. And so I just kind of applied this rule right here to the n value of 4. And so what you see on this term is you see a 4 factorial in the denominator. That's what 24 is. And then this isn't an 8 because I've factored an x minus 1 quantity squared out of that term. So the power has already gone down by 2. And then once this is written as a product, you can definitely cancel those. And then if we go down a little bit here, we want to write the general term. So here would be the first 4 non-zero terms in the Taylor series representation for f based at 1. And then what I did was I kind of re-indexed here. We had that cancellation up above here, right? This was the original 0 term, but that canceled with this. So I'm re-indexing. I'm saying, okay, here's my new 0 term. Here's my new n equals 1 term, n equals 2 term, n equals 3 term. What can I then write for my rule here? Well, my power is still 2 times n, right? 2 times 2, 2 times 3. My power is still 2 times n on the x minus 1. But my factorial in the denominator, this is 2 factorial, this is 3 factorial, this is 4 factorial. So I'm adding 1 to whatever n is and then taking the factorial to produce those factors in the denominator there. In part C, what they want us to do is they want us to use the ratio test to figure out what the interval of convergence for this Taylor series that we just found in part B is. And so the ratio test requires you to check this limit. And so I've just kind of taken a sub n plus 1, so that general rule that we were looking at the bottom of the previous screen with n plus 1 tossed in place of all the n's will give us this. And then rather than dividing by that rule, I've multiplied by the reciprocal of that rule. And then I just kind of simplified what we had on this term whenever you look at this equivalent limit. So I just distributed in that exponent, n plus 1 is n plus 2 inside the factorial that you see here. And then we can do a lot of cancellation. We have x minus 1 multiplied 2n plus 2 times in this numerator right here. We have that same factor, x minus 1, being multiplied together 2n times. We have 2 extra factors sitting in the numerator than we do in the denominator, so that I canceled all of these with almost all of the ones in the numerator. Whoops, I didn't want to do that. I wanted to do this. I'm left with 2 factors of x minus 1 left in the numerator, so that's what you see here. And then with these factorials, there's one extra factor present in this factorial that's not present in this factorial, and it's the factor of n plus 2. So this entire factorial is going to cancel with most of this factorial. We're going to be left with the factor of n plus 2. This limit right here involves n approaching infinity. X minus 1 quantity squared is unaffected as n goes to infinity, so I've factored that out of the limit. It's serving as a constant within that limit because it's unaffected as n changes. I did keep that within absolute values, and then my limit was a lot simpler. I had 1 left in my numerator and then n plus 2 in the denominator. On this next line, I realized, well, if I have x minus 1 being squared, that's always positive anyhow, so the absolute values aren't really doing anything, so I dropped them. And then this limit, if you put infinity in place of this n, you're looking at 1 over infinity, which is going to be getting closer and closer to 0. What the ratio test says is if your limit is less than 1, you converge whenever that happens. So if this is 0 and we take the product of 0 and this x minus 1 quantity squared, that's always going to be less than 1. Because you multiply this by 0, you get 0, and then that answer is always less than 1. So no matter what x is, you know your series converges because of the ratio test. So what's our interval of convergence? Well, negative infinity to infinity. And then in the last part of this, part D, what we want to do is we want to use the series for f that we developed in part B to figure out whether or not the graph of f has any points of inflection. This is kind of goofy. It does kind of tell us to use the series, so it kind of implies that doing the regular inflection point work with this function using quotient rules and chain rules to take 2 derivatives of this, it's going to be a mess. So we're not going to do that. We're going to see if we can figure out how to make the Taylor series work for us. So I just brought the Taylor series from B onto this screen. And if you're doing work for points of inflection, you're dealing with second derivatives. You have points of inflection anytime the second derivative changes signs, positive to negative, negative to positive. So I took the first derivative of this series, so the derivative of 1 went away, the derivative of this piece, well, I multiplied by the 2, and the over 2 and the 2 that I multiplied by canceled, and I'm just left with what was in that numerator. Technically, I should be using a little chain rule there because this is an inner function, but the derivative of this inner function is 1, so multiplying by the derivative of that inner function doesn't really affect anything. Similarly, I multiplied by the 4, so I had a 4 over 6, reduced that to 2/3, subtract 1 from the exponent, and then times 1 from using a chain rule doesn't affect anything, so that's why you don't really see that represented here. And then you multiply by this exponent, you're dealing with 6 over 24, which reduces to 1/4, subtract 1 from the power. And then I also took the derivative of the general term there, so the derivative of the general term, I'm multiplying by the exponent 2n. That's going to end up over this denominator. And then I subtracted 1 from that exponent. This is the first derivative right here. If we want to do work with inflection points, we're going to need the second derivative. So the derivative of this piece, this power isn't really doing anything. It's just kind of showing that this piece right here was the derivative of this term. But the derivative of x is 1. The derivative of negative 1 is 0. So the derivative of this piece is just a 1. Do the derivative of this piece, multiply by the 3. The 3 and the over 3 cancel, you're left with 2, subtract 1 from the power, and again the chain rule times 1 doesn't really affect anything, so it's not represented. Multiply this coefficient by that power, you get 5/4, subtract 1 from the power. I also applied the power rule to the general term, So I multiplied this coefficient by this exponent, so what I had there already now has this new factor within the numerator. It's this exponent, and then that exponent decreased by 1. And again, the chain rule doesn't affect anything. Multiplying by 1 doesn't change anything. What I notice about this second derivative right here is that I start with a positive 1 as the first term. Whoa. Try that again. Start with a positive 1 as the first term, and then all of my quantities that involve x, this one, all the ones that are skipped, even the general term right here, all of these quantities are going to be raised to even powers, right? Square, fourth power. If I double n, I get an even value, and if I subtract 2 from an even value, I'm left with an even value. So no matter what I put in place of x, and then subtract 1 from it within all these quantities, I'm always going to be raising that result to an even power. If you raise to an even power and you're dealing with a sum of a bunch of positive values, you're never going to have that second derivative being less than 0. That second derivative is always going to be positive. If your second derivative is always positive, you don't have any points of inflection. So that's probably the trickiest part of this. It's not too bad if once you kind of realize what you can do here, but that is 2009, number 6.